Now I'm going to discuss about the polygon law of addition vectors. So in general, to find the vector sum or resultant of number of vectors which lie in the same plane, we can follow any one of the two alternate methods. That means in general there are two alternate methods to find the vector sum or resultant of number of vectors which lie in the same plane. So the first method is to choose a coordinate system and we resolve the vectors into rectangular components along the coordinate axis. If all the vectors lie in the same plane, then we usually choose the plane containing the vectors as xy plane. Then we find the components of the resultant vector by adding the corresponding components of the individual vectors. That means whatever method I have discussed for the problems I have done in the previous two classes on finding the resultant of number of displacements. That is the usual method for most of the problems we do in finding the resultant of number of vectors in the same plane. But there is an alternate method to find the resultant of number of coplanar vectors. This alternate method is the polygon law of addition vectors. So now look at the screen here. So as shown in the figure, let us suppose there are 5 vectors A bar, B bar, C bar, D bar and E bar, all of which lie in the same plane. Let us suppose we know the directions and magnitudes of all the vectors. I mean, you are given the magnitudes and also the directions of these vectors. I mean, you know the angle between any two adjacent vectors. Then we can try to represent the vectors graphically in the same order. As I discussed in the past, in the triangle law of addition of vectors, in general, if two vectors are represented graphically such that the head of one vector is attached to the tail of the other vector, then they are said to be in the same order. Graphically, you can draw a vector at a different place in the diagram without changing its magnitude and direction. So you can draw the vector A bar this way. That means we draw this vector of same length as this vector in the same direction or parallel direction. Next, I draw a vector of same length or magnitude as this vector B bar and parallel to this vector. Graphically, you can represent the same vector at a different place in the diagram without changing its magnitude and direction for convenience of finding the resultant. That means you can attach the tail of vector B bar with the head of the first vector A bar. The similar way, we represent third vector C bar in this way. That means this vector is drawn parallel to this vector, third vector C bar, and of same length or magnitude. Such the tail of third vector is attached to head of second vector B bar. So they are in the same order. The same way, you can draw the fourth vector D bar in this way. That means this vector has same length or magnitude as this vector and parallel to this vector. That means tail of fourth vector D bar is attached to head of third vector C bar. The next we try to represent the fifth vector E bar, also in the same order. That means tail of the fifth vector E bar is attached to head of the fourth vector D bar. That means we are trying to represent the given vectors along the sides of a polygon, all vectors in same order. Then there are two possibilities. Sometimes the given vectors may form a closed polygon, whereas some examples the given vectors may not form a closed polygon. So in the given diagram, the five vectors do not form a closed polygon. To understand the rules of vector addition, we usually take the example of displacement vectors. Of course, all vectors are not displacement vectors, but whatever laws of addition are true for displacement vectors, they will also be true for other vectors. Let us suppose these five vectors represent five displacements given to the particle successively, one after another. This is the initial position of the particle, denoted by capital I. That means the particle moves along this line from this point to this point. So A bar represents the first displacement given to the particle. Let B bar denote the second displacement given to the particle, so that it is displaced from here to here. And C bar represents third displacement given to the particle. And D bar is the fourth displacement given to the particle. And E bar is the fifth displacement given to the particle. That means F is the final position of the particle at the end of five displacements. I is the initial position of the particle at the beginning of the five displacements. So the magnitude of the resultant displacement will be equal to the shortest distance between the initial and final positions. And direction of the resultant displacement will be from initial to final. That means when the five vectors A bar, B bar, C bar, D bar and E bar, if they can be graphically represented along the sides of a incomplete polygon, all taken in the same order, then the closing side of the polygon taken in the reverse order represents their vector sum or resultant, both in magnitude and direction. So in the figure here, the director line segment IF bar represents the vector sum of A bar, B bar, C bar, D bar and E bar. You can observe that tail of the resultant vector attached to tail of the first vector A bar, and head of the resultant vector is attached to the head of the fifth vector. That means the five vectors A bar, B bar, C bar, D bar and E bar are in the same order, but the resultant is in the reverse order. Means tail of the resultant attached to tail of first vector, and head of the resultant it attached to the head of the last vector. So in general, if a number of coplanar vectors can be graphically represented along the sides of an incomplete polygon, all taken in the same order, Then the closing side of the polygon taken in the reversed order represents their vector sum or resultant both in magnitude and direction. So as I was discussing the case where the given vectors in the previous diagram, I have shown the situation where the given vectors can be graphically represented along the sides of an incomplete polygon, all taken in the same order. Then the closing side of the polygon taken in the reversed order represents the resultant both in magnitude and direction. But in some cases, the given vectors may form a closed polygon. Let us consider 6 vectors. For example, let us suppose these 6 vectors represent successive displacements given to the particle. Let P bar denote the first displacement given to the particle. That means the particle moves from this point to this point. Let Q bar represent the second displacement given to the particle. That means it moves from here to here. Let R bar represent the third displacement given to the particle. Next, the fourth vector S bar. That means we are representing all the vectors in the same order. So when all the given coplanar vectors are represented in the same order along the sides of a polygon, in some cases you may get a closed polygon like this. That means in the given figure, the 6 vectors are represented along the 6 sides of a hexagon, all taken same order. In this case, magnitude of the resultant will be 0. It can be understood this way. If you assume that all the 6 vectors represent 6 displacements given to the particle, that means let us suppose this is the initial position of the particle. So P bar is the first displacement, Q bar is second displacement, R bar is third displacement, like that. After completing the 6 displacements, the particle again returns to the initial position. So when the final position of the particle at the end of 6 displacements coincides with the initial position of the particle at the beginning of the 6 displacements, then magnitude of the resultant displacement will be 0. That means in this figure, the vector sum of P bar, Q bar, R bar, S bar, E bar and F bar equal to 0 vector. That means in general, if a number of coplanar vectors can be graphically represented along the sides of a closed polygon, all taken in the same order, then the magnitude of the resultant is 0. So next I am going to discuss 2 special cases. In the case of polygon law of addition of vectors, that means you may be given a problem where all the vectors may have same magnitude. And for example, if there are n forces with same magnitude, such that second force makes an angle of 360 degrees by n with the first force, and third force makes an angle of 360 degrees by n, or 2 pi by n radian. With the second one, and so on. And fourth force makes an angle of 360 degrees by n with the third one, and so on. Then the n forces which have same magnitude can be graphically represented along the sides of a regular polygon of n sides, all taken in the same order. Then magnitude of the resultant of the n forces will be 0. For example, if you take n equal to 5, or let us take n equal to 6 otherwise. Let us suppose there are 6 forces of same magnitude which act on a particle simultaneously, such that all the 6 forces lie in the same plane. Then for 0 resultant, the angle between adjacent forces need to be 60 degrees. I mean, if you have 6 forces of same magnitude acting in the same plane simultaneously on a particle, such that second force makes 60 degrees with the first force, and third force makes an angle of 60 degrees with the second force, and the fourth force making an angle of 60 degrees with third one, and so on. Then the 6 forces can be graphically represented along the 6 sides of a regular hexagon, all taken in the same order. Then the magnitude of the resultant will be 0. So here, all the 6 forces have same magnitude in the given figure, and each force makes an angle of 60 degrees with the previous one. In such cases, the 6 forces can be graphically represented along the 6 sides of regular hexagon, all taken same order. Then magnitude of the resultant will be 0. That means in general, if there are n forces of same magnitude acting simultaneously on a particle, such that each force makes an angle of 360 degrees by n, or 2 pi by n radian with the previous one, then magnitude of the resultant will be 0. But sometimes you come across a similar situation but slightly different. In some cases, the number of forces may be 1 less than the number required for 0 resultant. For example, instead of 6 forces, you have 5 forces of same magnitude. That's about 3 Newton. Acting on a particle simultaneously, such that each force makes an angle of 60 degrees with the previous one. Let us suppose second force, just like in the earlier example, makes an angle of 60 degrees with the first one. Third force makes an angle of 60 degrees with the second, and fourth force makes an angle of 60 degrees with third, and fifth force makes an angle of 60 degrees with fourth force, F4 bar. But you have only 5 forces with same magnitude, for example 3 Newton, acting in this manner. That means each one making an angle of 60 degrees with the previous one. Then they can be graphically represented along the 5 sides of an incomplete regular hexagon. Then the closing side of the regular hexagon, taken in the reverse order, represents the resultant of the 5 forces, both in magnitude and direction. So the closing side of this regular hexagon will have the same length as any one of the other sides. That means in this example, the magnitude of the resultant will be equal to magnitude of one of these forces, which is 3 Newton. So you can write the general conclusion this way. If we have n-1 forces of same magnitude acting in the same plane, such that each force makes an angle of 360 degrees by n or 2 pi by n radian with the previous one, then the magnitude of the resultant will be same as the magnitude of one of the forces. So I would like to once revise my discussion which I have done about the polygon law of addition vectors. That is, I would like to show you the summary of the discussion about the polygon law of addition vectors. And those who are interested to copy the notes, they can take a pause and copy the notes from the summary I am going to show you now. So look at the summary of the polygon law of addition vectors. If a number of vectors can be graphically represented along the sides of an incomplete polygon, all taken in the same order, then the closing side of the polygon taken in the reversed order represents their vector sum or resultant both in magnitude and direction. So in this figure I have shown 5 vectors A bar, B bar, C bar, D bar, E bar, whose magnitudes and directions are supposed to have known, which are represented graphically here along the sides of a incomplete polygon. That means the direct line segment IA bar represents the first vector A bar, and tail of second vector B bar is attached to head of first vector A bar, like that. Tail of third vector C bar is attached to head of second vector B bar, and so on. Tail of fourth vector D bar is attached to head of the third vector C bar. So the closing side of the polygon taken the reverse order. The closing side is the length, that is the side I obtained by joining these points I and F. taken in the reverse order represents the resultant both in magnitude and direction. So tail of the resultant, here attached tail of first vector A bar, head of the resultant is attached to head of the fifth vector E bar. So in the figure, the direct line segment IF bar gives you the A bar plus B bar plus C bar plus D bar plus E bar. The next conclusion, if a number of coplanar vectors can be graphically represented along the sides of a closed polygon, all taken in the same order, then the magnitude of their vector sum or resultant is 0. So in the figure I have shown 6 vectors denoted by P bar, Q bar, R bar, S bar, E bar and F bar along the 6 sides of a closed polygon, all taken in the same order, and the resultant of the 6 vectors will be 0. It should be actually 0 vector, the general way here, or more preciseness, you can put bar symbol here. Look at the special cases. Case 1. Suppose if n coplanar forces of same magnitude act on a particle simultaneously such that each force makes an angle of 360 degrees by n or 2 pi by n radian with the preceding one, then the magnitude of the resultant will be 0. Then you see the case 2. Suppose if n-1 coplanar forces of same magnitude act on the particle simultaneously such that each force makes an angle of 360 degrees by n with the preceding one, then the magnitude of the resultant will be same as the magnitude of one of the forces. So I would like to show you an example based on these special cases. Look at the problem based on these 2 special cases. If 9 coplanar forces of same magnitude 6 Newton act on the particle simultaneously, what is the magnitude of their resultant? Each force makes an angle of, there are 2 parts in the question. First part of the question, 40 degrees with the preceding one. Second one, 36 degrees with the preceding one. Come on, think about the question here yourself. You can answer it orally. Not much mathematical calculation is needed for this problem. I have given you 2 special cases. Once again, try to recollect those cases. In the first case, that means if there are n forces of same magnitude, acting simultaneously on a particle such that each force makes an angle of 360 degrees by n with the previous one, then magnitude of the resultant is 0. Now, when the angle between adjacent forces, successive forces, 40 degrees, how many forces are required for 0 resultant? 360 by 40. That is 360 by 40 will be how much? Equal to 9. That means in the first part of the question, there are n forces equal to 9, n equal to 9 coplanar forces of same magnitude, such that each force makes an angle of 360 by 9, which is equal to 40 degrees with the previous one. Then they can be graphically represented along the 9 sides of a regular polygon, closed polygon, all taken same order. So magnitude of the resultant in the first question will be 0. Coming to the second question. In the second question, the angle between any two adjacent forces or successive forces is 36 degrees. So for this angle, how many forces will be required for 0 resultant? 360 by 36. 360 by 36 will be 10. But here you have 9 forces only. You look at the screen once. So in the second part of the question, you are given that each force makes an angle of 36 degrees with the previous one. Therefore, the number of coplanar forces in this case required for 0 resultant will be 360 degrees by 36 or 10. That means if you have 10 forces of same magnitude acting in the same plane, such that second force makes 36 degrees with the first force, and third force makes 36 degrees with the second force, and so on. That means each force make an angle of 36 degrees with the previous one. Then magnitude of the resultant will be 0, as the 10 forces can be graphically represented along the sides of a closed polygon, all taken in same order. But here the number of forces is not equal to n. The number of forces in this example is 9. That you can write as n minus 1. Here n equal to 10. As I discussed in the case 2, that in general, if there are n minus 1 forces of same magnitude acting simultaneously in the same plane, such that each force makes an angle of 360 degrees by n with the previous one, then magnitude of the resultant will be same as the magnitude of one of the forces. So here magnitude of one of the forces 6 Newton. That means for second part of the question, answer is 6 Newton. But for first part of the question, the answer is 0. That means here the 9 forces can be graphically represented along the 9 sides of an incomplete polygon of 10 sides. The polygon with the 10 sides we call decagon. That means the 9 forces can be graphically represented along the 9 sides of an incomplete decagon. So the magnitude of the resultant will be equal to the length of the closing side, which will be same as the length of one of these other sides. So in my next class, I am going to discuss about the subtraction vectors.